Okay, for section 2.5, I'm just going to do 3 problems, 20, 23, and 45. So let's take a look at 20. These are all derivative problems. And what I want to emphasize is when you take derivatives, you do need to keep track of the terms, right? That's the key to this whole thing, is keeping track of the terms. And sometimes you can do something fancy. And make things work out, but other times you can't. So let's just do this. Let's see if we can do this one directly. All right. So what we have here is sine x minus cosine x over sine x plus cos x. So you do want to kind of break this up into pieces. I can write this as I can look at the first piece and the second piece, right? So I can take the derivative of both of these. So let's take the derivative of the numerator, sine x minus cosine x. If I take the derivative of this, I could write this as ddx, or I can write it as a prime. I'm sure you've seen the prime notation before, so I'm going to use that here. Derivative of sine is cosine, and derivative of cosine is minus sine. So I have this here. Okay. Now, you look here that the derivative of the top is the bottom. That's actually a tip-off, but we'll go ahead and do it the long way. All right, so here we have sine x plus cosine x, and we'll take the derivative of this. All right, so here we have something similar. This just becomes derivative of sine is cosine x, and then this becomes minus sine x, right? Okay, so we can go ahead and use the quotient rule. Or like I like to say, it's the product of it's the product and reciprocal rule. But let's go ahead and use the quotient rule. Quotient rule has the bottom squared on the bottom. And then it's the derivative of the top times the bottom minus the top times the derivative of the bottom. So derivative of the top is sine x plus cosine x. And the bottom is just sine x plus cosine x, so that actually works out quite nicely. Then I have to subtract the top times the derivative of the bottom. So that's sine x minus cos x times cos x minus sine x. Okay. All right. Now let's see, what about this one here? In fact, this, if I can break this up into 2 pieces, right, this first piece is going to be 1, right, because this numerator and this denominator are the same. And then this minus here and this minus here cancel, so I'm going to get plus sine x minus cosine x squared over sine x plus cosine x squared. So you might wonder if you can simplify that. You probably can. Let me think about that for a minute. Well, one thing I can do here is notice that when I square this out, the sine squared and the cosine squared, they do some nice things. So let's take a look and see how that works. So here we get the 1 on the front. And there's actually other ways to do this. I could have expanded these out and done some cancellation here, but I can go ahead and write this as 1 plus, then this becomes sine squared minus 2 sine x cosine x, forgot the x here, and then plus cos squared x, and then this becomes over sine squared x plus 2 sine x cosine x, and then plus cosine squared x. Now you can recognize that sine squared plus cos squared, right? So this becomes 1 over, these two combine to a 1. 1 minus 2 sine x cos x over 1 plus 2 sine x cos x. All right. And what you can do here is just, now you can put these over a common denominator back again. And it turns out I shouldn't have split it up at the beginning, but sometimes that happens. You don't do the right thing. So you get 1 plus 2 sine x cos x plus 1 minus 2 sine x cos x. And that's over 1 plus 2 sine x cos x. All right, so that turns out on the top I get these canceling, so I just get 2. And I could write 2, this 2 over 1 plus 2 plus sine 2x. If I could write it that way, that's fine. There are other ways to write it, but that's one answer. Okay, so there's not just one way to write it, but that's one answer. I could possibly have done something easier farther up, but you just keep working, looking for patterns. Of course, when you have sine and cosine and you have squares, you have a good opportunity to square out and get sine squared plus cosine squared. All right, so let's look at the next one. Next one was 23. Let's take a look at that one. And let's pull that down. '23 is here. All right, now you got all this stuff. This looks really terrible to take the derivative of that. But it turns out that when you take derivatives like this, it's kind of a natural extension of the product rule. Right, here we go. Let's see what this, so I can write this, I want to take the derivative of this. I'm just going to write some shorthand, u, v, w, z, and I'll write the prime notation. All right, so I can write this as the derivative of u times vwz. Whoops, sorry, that should be a v. Let's work this up step by step. vwz, okay, it's the prime of this. So this is equal to u prime times vwz plus u vwz prime. Okay? All right. So this one is done. This one we still have to do. So this is going to be u prime vwz plus u. Now let me split off the v and leave the wz, right? So that becomes u times, here we get v prime wz plus v wz prime. All right. And you can kind of see where this is going. You just keep on taking this step by step and you get to a nice place. Now it turns out you can use this one for number 24. Number 24 is a special case of 23. All right. So you can use that. All right, let's move on to the last one I was going to do, which is 45. And that's over here. All right, so this is a little bit complicated word problem. Whenever you have a word problem, you should draw a picture. So here we've got this. Plane starts its descent from height y equals L at y equals h at x equals minus L to land at 0, 0. Okay, so let's not delay. Let's go ahead and start drawing stuff. All right, so the plane starts at x equals minus L and y equals h. All right, so those are my axes. So this is my x-axis and my y-axis. And let's make the plane a different color so that it's, because we can. Oops, sorry. What happened to my mouse? There we go. Okay. Let's use blue. All right. So it passes through 0, 0 here. And it also passes through minus LH. All right. And we want this to be smooth. Smooth means we start out horizontal, it's cruising horizontally, and it's going to go something like this. Right? We want something like this. Now we know you can kind of fill this in with a cubic curve, something like that. So that's kind of what we want. All right. This is going to be the maximum. This is going to be the minimum. All right. Now we can use that to kind of figure things out. In fact, here we have a double root. If you think about that, this is a double root. So that's really telling you what your cubic is going to look like. But let's go ahead and do it the calculus route. We want y equals ax cubed plus bx squared plus cx plus d. Now, what do we know? Well, let's look at the information here. Here we say the landing is smooth. So what does that mean? That means, for instance, when I land at x equals 0, I should not have any bumps. That means that this curve should be completely horizontal. And of course, it should also pass through 0, 0. All right, so that's the first thing. It passes through 0, 0. Let's start with that. All right, so that's something that we can say. We can say y of 0 equals 0. That's one thing we definitely know. Okay, so that's going to give me, let's see. So I plug in x equals 0. I'm going to get 0 equals, now if this is 0, 0, 0, this is d. So d equals 0. Great. All right, now I also know that y of minus L is equal to h. So I know that. That's a good thing to know. Right, so that's going to be a little bit more complicated. So h equals a times minus L cubed plus b times minus L squared plus c times minus L. Now I don't need to include the d because I already know that's 0. All right. Now let's work on the smooth aspect. Here we can see when we reach 0, as I said, there are no bumps. So we actually have that dy dt at 0 must also be equal to 0. Now what's dy dt at 0? Well, we have to take the derivative here. Now we have our new power rule where we have ax cubed, the derivative of ax cubed is equal to 2ax squared times dx dt. Then we have plus 3x squared times dx dt. And then this is going to be plus 2bx dx dt. And then I have plus c dx dt. Now I happen to know that dx dt is v. But that cancels out on both sides because if I divide by a non-zero number, I still get 0. So I get 0 equals 3ax squared plus 2bx. Oh, but I forgot something here. This is when x equals 0. Okay? No, when x equals 0, so that tells me that 0 equals c. Great. Okay, so d and c are both 0, so all I need is a and b. All right? So this c is going to go to 0, so we just need to solve the a and the b. All right? The other thing I know is that when it descends smoothly. So I know that dy dt, when x is equal to minus L, is equal to, or let me evaluate this here. Sorry, let me say it this way. Dy dt is equal to 0 when x equals minus L. Now I can use the same expression here. This one was for x equals 0. Okay. Notice I don't actually know what t is, and it really doesn't matter because this doesn't depend on t. All right. So now I have this simplified. This c minus L goes out. I don't need that anymore. So I'm just going to remove that here. That goes out. Okay. Because I have this. All right. So if I take the derivative, I can use the same expression. So I have that 0 equals 3a squared, 3a. And now here, this is when x is equal to minus L. Then I have 2b. And then this is minus L. Now I also have the v's here, but those are going to cancel out. All right? And I forgot the b here. All right, so we have two equations here. We have an equation with h. We have an equation with no h. All right? So this will give me a and b. So I can use this to solve a and b. All right, so the takeaway here is you want to take the information that's given you in the problem and translate it into equations. Now, I had this position that was one position, and I saw from the picture this was another position, and then the smoothness gave me that these two derivatives were zero. Right? So that gave me all that I need, and I was able to solve, and I could easily solve for A and B, depending on H and L. Okay, so that's it for now.